upload it. Okay, or writing steps, something to. Okay, let me look at the questions. Thank you. It didn't allow you before, but right now with the change it should, and after the class you can do it if you want to. Let me know if it doesn't still, Natalia, because you're saying that it would allow you for link, but not the saved. With the new change, it should allow, but.
Okay, I'll let you know. I'm gonna try again because I already have the problem on the paper.
Okay.
Thank you.
Taylor, just submitting that drawing for question 1 should be good. Okay, because I will grade the question 1 from the second submission. Let you upload the link to an image and the first question of the pre-lab. Yes. Will not let you browse your computer for one. Okay. The mole ratio so far with all the reactions that we had, it has been 1-to-1 ratio for all the mole ratios with the reactions that we had. For the nitration, you start with methyl benzoate and you get 1 methyl benzoate if you're talking about experiment 40. Okay. Any other questions you might have? No? Okay, I'm going to go to the lab manual and start with the experiment, experiment 15. The reaction for the experiment is reduction of ketone. When you reduce a ketone, it will change to secondary alcohol. If you have aldehyde, it will change to primary alcohol. In this reaction, you do have the ketone or fluoronone for as a reactant. The sodium borohydride is reducing agent. Alcohol, it could be methanol or ethanol, is the solvent because you want this to be able to react and mix well. So you are using alcohol as a solvent. The product is going to be fluoronol, which is the reduced product from the fluoronone. The ratio is 1-to-1 for calculation of percent yield recovery or percent yield. And your reducing agent is sodium borohydride. The mechanism for this reaction is a nucleophilic kind of attack from the hydride ion. So when you have sodium borohydride, H minus or the H minus is going to act as the nucleophile. So with the nucleophile attacking the, let me bring that, okay, attacking the carbonyl group, the pi bond breaks over the oxygen. You get alkoxide. You protonate the alkoxide and it changes to alcohol functional group. So when you're talking about hydride ion, is a H with minus charge or hydrogen with 2 electrons. And because of the negative charge, it is acting as a strong nucleophile and it can attack the carbonyl group. The type of reaction, it's like addition reaction or reduction reaction because it's adding 2 hydrogen. Hydride is coming from sodium borohydride, and then the other oxygen to protonate the alkoxide is coming from the solvent. So you have alcohol as the product. This reaction here, it shows if you have a ketone, it will give you a secondary alcohol. If you have aldehyde, it would change to primary alcohol. When we are doing this reaction in lecture, you are concerned about the reactant, reagents, and product. When we perform experiment in the lab, as we have done in the past for the last few experiments, we want to make sure that we have a method to identify our compound, its purity, and identity, basically. So we have to use an evidence. It has to be evidence-based, so we must have an evidence, which could be a physical property, or it could be a spectroscopy technique of IR. Other spectroscopy that could be used, but the ones that we are using in the lab is the IR. So we have the like melting point, boiling point, that is physical properties. That we can use the melting point, for example, for this product, and compare that to melting point of the product in the reference number or the literature value for the melting point of this product, and decide if the product is pure or is not pure. If the melting point of the product is lower than the literature value and the melting range is broad, that means that the compound is not pure. But if you have a melting point that is close to the literature value for the product, then that identifies you have the product. The percent of impurity, the greater amount of impurity, yes, also the percent of impurity, the higher impurity you have, the more broad the range of the melting point is going to be, and also is going to be much lower than the literature value. Big. How the IR is used in this experiment is that you take the IR of the product and you have the IR of the reactant. When you are given the IR spectrum for the product, you don't have to interpret every single peak. What you are looking for is more of like comparison. So for the reactant, which peak do you expect for the reactant that doesn't happen for the product, that doesn't show on the product? A 1780. So for reactant, around 1700, okay, 1700, around 1700 for ketone. And what do you see for the product? What would you have for the product? For product that is distinct for product that does not show for the reactant, you would have a peak around, what's the functional group for product that is new for product and doesn't show for alcohol? So for product, 3300 peak for OH. So if you take the IR for product, you expect to have a peak, broad peak at the 3300 area. That is a new peak, and it doesn't appear, it doesn't exist for the reactant. So 1700 should have disappeared, and the new peak at 3300 should appear to show that the product has formed. And if the 1700 completely disappears, the peak at 1700, OH is broad, yes. So if the peak at 1700 completely disappears, that means there is no impurity as well. So because if you have leftover of the reactant mixed with the product, the peak at 1700 would still show. So if the peak at 1700 disappears, that means there is no leftover of the reactant and your product is pure. So IR, it can determine the functional group. At the same time, for monitoring the reaction, going from reactant to product is a very strong tool, and you can determine based on the functional group of the peaks that are specific for the functional group of the product, and they are not in the reactant. So you are going to also calculate the percent yield. To determine the percent yield, first of all, you have a 1-to-1 ratio. Again, you're using the same procedure for going from number of moles of reactant to moles of product, and then mass of the product. Mass of product that you get in theory, that would be theoretical yield. Experimental yield is the mass of the product determined in the lab. And actual divided by theoretical, that gives you the percent yield. The product today, let me look at some of the procedures, then I can explain why it's so fluffy and it doesn't dry really. So we talked about the reduction reaction or reducing agent, which is sodium borohydride we are using. Lithium aluminum hydride is another reducing agent, and that could be used more of carboxylic acid, and acid derivative is stronger than the sodium borohydride. But sodium borohydride is good for aldehydes and ketones. You learned that in lecture organic 1, end of organic 1 or beginning of organic 2. So this is one of the reactions that most of you already know about. And we looked at the 2 reactions, the possible reaction mechanism for the reaction. In this reaction, you are using HCl. Can you tell me what is the purpose of using HCl? Basically, after the reaction is done, you're using HCl. The use of HCl. Okay. So at the beginning, you start with the fluoroanone, which is a yellow color solid compound. You're adding the solvent of ethanol and a reducing agent of sodium borohydride. When you add those, you're going to stir it for about half an hour. And visually, you could stop the reaction and decide that the reaction is done when there is no more yellow color appearance. So this appearance of yellow color and product, if it's white color, white precipitate, that means you have the reaction has been complete, and that's like qualitatively you can prove that. But melting point and the IR is going to confirm that the product has formed completely. After the 30 minutes or the extra 10 minutes or whenever the white color appears and the yellow color has disappeared, then you are going to add that to HCl solution. And as I think Victor has responded, the HCl is going to destroy the leftover of sodium borohydride. Because in this reaction, fluoroanone is your limiting reactant, and sodium borohydride is the excess compound. We want to remove the excess compound, just like the experiment 12. To remove permanganate, you are using sodium bisulfite. Here, because then permanganate was excess compound. Here, sodium borohydride is the excess compound, and you want to remove that. You are destroying by using HCl. Is to remove the excess of sodium borohydride. When you add the sodium borohydride to HCl, it's going to generate hydrogen gas. Lots of bubbles is going to form. That's why it's asking you to do it under fume hood, and no flame should be on at that point. But the problem that is going to cause, it makes the product very fluffy, and it is like whipped. And it's going to capture lots of gas within the product, within the solid compound, and that's why when you try to vacuum filter this product, because it's fluffy, it's going to it's going to make it very hard to filter and get all the moisture out. So for that reason, the time that I did the experiment, I couldn't measure the mass of the product, a final mass of the product that same day. So you're going to find the mass of product on the following video, or if I'm going to also look for the mass of the product and then write in the announcement what's the mass for final product. But if you are writing your lab report before the announcement is up, you can look for the video for experiment 16 or the chat area for experiment 16 and find the mass for the product for experiment 15. And I did explain there, most likely, that's why I cannot use the mass that day, because it doesn't dry. And if it doesn't dry, the mass is going to be much higher than 100% recovery. And we have to dry it before we measure the mass. So after the HCl, you are going to filter it, and if needed, to recrystallize the sample with the recrystallization solvent, which is a 1,2.5.5 water methanol solution. And after the recrystallization, you are going to vacuum filter it, dry it for like 5-10 minutes in the oven for with 100 degrees Celsius, or let it air dry for complete drying, and measure the mass, calculate percent yield, and the IR spectrum should be in the folder already, and I will check it, double check it now. Let me answer your questions first, or look at your comments first, and then I will go back to speed dry. I think I did that for the melting point. So with the speed dry, you just take a small piece and place it in the oven for the melting point. That's what I did with the experiment. But the other is just, it's like so spongy that it doesn't, it's not easy to the water is actually trapped between the particles. And sometimes I measure the mass and I see that it's much higher than the theoretical yield. I let it dry overnight. I do use the oven. But keep in mind, when you use the oven, the top layer and the bottom layer, it can burn. And then inside it can, if it's like too much trap. So when you watch the video, you might see that it's like a thick layer of the whipped product. Is not like a powder. Supposed to conduct the IR. Okay, what I did, I took a small sample of it, and I placed it within the filter paper and paper towels. I took the moistures out. A small sample, it dries up with 5-10 minutes using the oven. But when you have a bulk of a sample, it didn't dry. But I did make sure the sample was dry before the taking the IR of the sample. Okay, any questions? Any questions about the experiment? Okay. Victor, you had a question about the pre-lab. Did I answer your questions, or you still have a question about the pre-lab? You could just say the question number, I can look for it. Trying to say is, what are you looking for in the...
Is this the... Okay, the questions 2 and 3. So the thing is, I couldn't figure out where to find it in the actual lab manual, so I had to go and look for like charts online, and I thought all the information could be obtained from the lab manual. I mean, if we have to go somewhere else.
Experiment 17 of the experiment, yes, experiment 17 of the lab manual. It contains all the charts for the IR and for the NMR, and that can help you.
Okay.
And it is the, sometimes the lecture, is supposed to move at this time. Actually, the IR should have been covered in lecture. And we're trying to kind of match with the, the schedule of how they're teaching, the order of the chapter that is taught in lecture as well.
Okay.
It's kind of hard to have an exact match, but the information is provided in experiment 17.
Okay. I'll look around.
Sure.
Thank you.
And your question, Natalia, is that any lecture should cover the IR spectroscopy soon. Yeah.
I'm sorry, you said there are charts on the lab menu for us to reference from?
You have in experiment 17 in the lab manual, yes.
Oh, 17.
Yes, 17. If you look at experiment 17, which it covers IR, you can use those charts, or chapter 12 from the weight book that it covers IR. Also 12 and 13 from the weight book. At this point, I thought chapter 12 should be covered because it's past like 6 weeks of the semester, right? The lecture, which is any of the lecture covered IR spectroscopy?
Oh yeah, mine has. I just didn't see the chart. I thought it was still on the 15, the one that we're doing now. I didn't realize it was 2 ahead. It's just easier to look in a reference with the lab.
Yes, in the lab is in experiment 17. Okay. But I really can't imagine you're still on chapter 11, and chapter 11 is supposed to be the first chapter in Organic 2 lecture. That's you have a long way to go. Not enough time to cover all the chapters.
We did IR. It's just that we're actually not doing an order.
No, I was talking to Julia. Yes, I was actually.
Some professors don't do the chapters in order.
Okay.
Doctor, one more question. Should we? Are there any other chapters in the book that we might need to reference in the future, or is it only 17? Do we have to stick around somewhere else? Like,
no,
for experiment 16, we might have to go to 19, or is that it?
No. If you could have just simply searched for these questions, that would have helped also. Okay. So you didn't have to.
I did a search online. I was looking around.
That's good.
But the thing is, I'm trying to use your content and not somebody else's content to answer questions. But if I have to go somewhere else and you're okay with it, that's all I need.
I'm fine. No, I am 100% fine with that. Is a pre-lab question. You have open book, open resources quiz, so it's okay. And then, Cherise, to answer your question one more time. I think you talked about the use of the IR for this experiment. One more time, you are trying to look at, let me bring the question again, the equation again. You're trying to compare the reactant to product. I mean, I'm not expecting you to interpret every single peak from the reactant and product, but look for the point of difference. The point of difference is the functional group of CO double bond for the reactant versus the OH group that you have on the product. So for the IR spectrum, what's going to happen? The peak at 1700. So you have a 1700 location for product. I'm sorry, for reactant. I'm writing, so make sure that I write the right thing. Location for reactant. But 3300 is specific to product.
Doctor, are you sharing your screen? Are we supposed to see what you're writing?
I'm writing on the chat area. Do you have the chat open? There is a purple button at the on the.
Yes.
Okay. So the 1700 location for the reactant and 3300 is specific for the product. So when you go from reactant to product, the 1700 should disappear, and the 3300, the peak at 3300 should appear. Okay, and then question 3. What was question 3? Was that for the NMR? Yes, NMR, the peak for NMR for OH, that also is in the chapter, is experiment 17, and we are only using for application. The reason I put these questions here, because for the exam, I mean, I use the application of the IR and NMR, but if I go to 17 and then I don't have the reactions, the actual reactions to use the IR, NMR, and by the time we are in experiment 15, really, I was expecting that the chapter 12 to be introduced at least to the in lecture. So that's what we are using as a reference. Yes, and your response, Julia, that is correct. And it is a broad, small peak is for OH group. That shows in between. There is no specific location for that. Is anywhere between 2 to 5, surely for OH it will show. And if you did search for the answer, that is great. There is no problem with that. And soon, when we talk about experiment 17, you would actually, by then, I just hope that at least IR is covered in lecture. So you have more exposure to the IR application for the IR. And I do explain it also. Yes, Charisse, your question.
I guess I just want to understand, so after we're done with our lab report, run the IR spectrum, are you just asking us to explain what would occur when we run it in our lab report, or you just want us to have an understanding?
I want you to bring the data. Why are we using data? Why are we using IR for? Can you tell me what's the purpose of using IR?
Okay.
What is the purpose of using of IR? It should be written in the lab report. The reason we are using IR in this experiment is to confirm that the product has formed, right?
Right,
and
I understand. I just wasn't sure if you were expecting.
Okay. I'm just explaining to whole class, like if you are the parts of the part of the IR interpretation that we are using for the experiment is like a reaction specific, basically comparing the point of difference for reactant, going from reactant to product.
Okay, because I didn't include that in. Okay, I didn't include that in my lab 13 report because I just thought because we weren't able to do it in the class, I didn't know that you wanted it in the report. So can I resubmit that with that information? Or will it?
We didn't do that in class. The IR, it was provided in the folder, right? We did talk about it during the pre-lab discussions. If you go back and open the pre-lab discussions for 2 weeks ago, when we talked about experiment 13, I showed you the IR spectrum, and I said the location of the exact peak when the ester was formed, it's moving from 1700 to 1718. That shows that the product has formed. Right?
No, yes, I understand that. I just didn't know that you wanted us to put it in the lab report because we weren't actually running a physical IR spectrum because we are not in a physical lab. So I just thought you were just telling us this. I didn't know that you wanted it in the actual data calculations. So that's why I didn't submit it. I just misunderstood what you meant by including that data in our lab report.
So the value of that, okay, regardless of, this specific question, I'm just answering general to the whole class. The value of the data is coming from IR, and melting point and the percent yield are exact the same. These are the data that is showing us the product has formed. So if we don't have the evidence that the product has formed, we can't defend our case that yes, this is the product and I know that the product has formed. The liquid that you measure the mass in experiment 13, it could be water. How would you prove that you have actually ester in there? Or if it's contaminated with water, the only reason you can prove that it's ester and not contaminated ester with alcohol or water or anything else is that there is no OH group there. That means you don't have leftover of acid, you don't have water contamination, and the location of the CO double bond, it shows that it has shifted to higher number, which is 1718 is specific for a conjugated ester, and that's why I showed the location of that peak. Okay. Other questions about this experiment 15? Any other questions that you might have? Okay. Let me call for attendance. You can watch the video. I hope that you all have access to the, have to access the recorded pre-lab discussions. It's good idea, like in case if you forgot, because I do repeat sometimes and often what needs to be on the data, as the data for this experiment is going to be the IR, the melting point, and the percent recovery or percent yield in abstract, in conclusion, and discussion. Brianna, this is for attendance. Brianna. Thank you. Victor.
Here.
Thank you. Ahmed. Ahmed, are you here? Okay. Michael? Yeah. Karina? Alavia? Julia? Melissa? Denise? Therese? Jeanne? Cindy? Natalia? Jones? Taylor? And Christopher? Maria from 1230 class? Maria? Okay, perfect. Just in case, I'm just reminding you guys, I am teaching another Organic 2 lab on Wednesday at 12:30. So in case for any reason you missed the class on Monday 3:30, you can make up during that same week, not the following week, during that same week on Wednesday at 12:30. But you need to send me an email before the class on Wednesday to ask for the link, so you can log in or join the meeting for the pre-lab discussion meeting. Perfect. Okay, if you have any questions, you may stay to answer your question. If you don't have questions,